In our last video, we learned about magnification and how we can use lenses to bend light rays to help make objects appear larger, right? We form a virtual image, we get a bigger projection on our retina, and we get a bigger picture, okay? But magnification by itself is not enough for us to be able to observe the very fine details of these very small things we're going to be looking at in histology. Magnification alone will not do it. Let's check this out. Look in the center of the screen. You see a blue circle. Inside that circle, you see something small and black. It's really small, so we need to magnify it. But if we just magnify, right, we might end up with something that looks like this. It's kind of like a double hump oval or something like that. I don't know what you would call that, right? But we weren't able to distinguish that that's actually two separate dots. If you get real close to the screen and look, you'll see that's two dots. And we can't see that with just magnification. No, what we need is magnification plus resolution. So we not only make the circles bigger, but we also keep them from overlapping. They're not as fuzzy. We can distinguish that they're two separate objects. So magnification plus resolution not only makes the images larger, but it preserves the detail. It allows us to distinguish separate objects as separate. As a matter of fact, the definition of resolution, right, which is the kind of the limit of a lens system, is the distance between two objects that they can be discerned as separate. So all of our lens systems that we're going to use are going to have a finite limit on resolution, and that's really down to physics. So there's a few factors involved in determining what the resolution limit of a lens system. So let's look at those factors. Okay, the first thing we have to take into account is the wavelength of our illumination radiation. In our case, it's going to be light. So we're looking at the wavelength range of visible light. We're looking at the visible spectrum. Okay. The Greek letter eta refers to the refractive index of the lens, or the medium through which the light is passing. Anything through which light is passing is going to have a refractive index. And so that's going to be a constant value based on the materials the lens is made out of, whether or not it's immersed in something that is going to refract light, like water or oil. And then finally, sine theta refers to the angular aperture of the lens. And that's essentially the light gathering capability of the lens. How wide an angle is that lens able to gather light from? And so if we put these together, you get the equation that you see on the left-hand side of the screen. 0.6 lambda divided by eta sine theta. Now for our convenience, eta sine theta is usually combined into a single value known as the numerical aperture, which along with magnification is almost always printed on the barrel of a microscope objective lens. So it's kind of hard to see in that picture, but if you look there at the tip of the blue arrow, you'll see it says L50x. So the 50x has to do with the fact that it magnifies things 50 times, but that 0.60 there indicates that this has a numerical aperture of 0.6. So if you multiply eta and sine theta for this lens, you would get 0.6. So let's work this out in practicality. Let's determine what is the actual limit of resolution that we can get out of a microscope using visible light as its illumination source. So let's just remember that lambda is our wavelength, and the lowest value for lambda that we can get with visible light is about 400 nanometers. Below that, you're into ultraviolet light, and we can't see that. Refractive index, so an ideal lens system, that is with the best possible lens in a refractive oil, the best we can do is 1.3, and because sine theta is a sine function, its maximum value is 1. Remember, we want the lowest possible number here. Okay, the lower the resolution number is, the closer two things can be, and we can still see them as separate. Okay, so we're going for a low number. So let's plug some stuff in here. Okay, so if I can get my pen to work, here we go. So we have 0.6. Our lambda value is 400 nanometers. Okay, so I'll just go ahead and leave the units in there. Very good. So, and then we're going to divide that by an eta value of 1.3 and a sine theta value of 1. So this is the ideal. All of these are optimized the best you can possibly get with white light. So 0.6 times 400 is equal to 240. Why am I writing a separate zero? I don't know. Okay, so that's going to be about 240 nanometers, and then 1.3 times 1 is, of course, 1.3. So 240 divided by 1.3 is like 184.6 or so. Let's just call it 185. So for an ideal lens system, our maximum resolution, right, the best we can do, the closest two things could be, is 185 nanometers apart. Now keep in mind, this is an ideal lens system. In actuality, we're using, full visible spectrum light. We're not just using blue light, so we're going to have higher wavelengths. Rarely are we going to get a lens with a numerical aperture of 1.3. You saw that 50x lens had a numerical aperture of 0.6. So for practical purposes, the lower limit on resolution in an optical system is about 200 nanometers. So roughly 200 nanometers. So while you can magnify infinitely, your ability to resolve is limited by the wavelength of light and other factors such as the refractive index of the lens. So we will get into other ways that you can get that wavelength lower using things that aren't visible light, but I think that's a video for another day. See you later.